And welcome back. This is part 2 of lesson 5 of Fluid 2000, hydraulic fluid power. And this presentation is on rotary actuators, or otherwise known as hydraulic motors. As mentioned before, most of the hydraulic power is used in linear actuators. However, there is some use for hydraulic motors or rotary actuators, especially if you have a self-contained piece of equipment and you can power it by one power source as opposed to two, and where the motor needs to have excellent torque speed characteristics through a wide variety of speed regulations. And hydraulic motors are really good for that, especially on processes that are stationary. On moving equipment, not so much, but they really come under their fore on large torque, low speed applications. And of course, hydraulic motors convert the movement of pressure of fluid into rotary mechanical shaft rotations. Basically, what you're going to be doing is you're going to be exchanging that pressure drop for mechanical torque. And a lot of times, the design of the pump and the motor is identical, and they're almost interchangeable in a lot of cases. However, of course, in a pump, you're trying to maximize the amount of volumetric flow through. And in a motor, you're trying to control the amount of torque. So pressure in a hydraulic fluid entering the inlet part of a motor determines its force or the torque output. So the higher the pressure, the more torque I'm going to be able to develop, obviously. The flow rate of it going through the inlet port determines its speed. So the pressure at what it's at is going to give me my torque, and the flow, how fast it's going through, is going to determine the speed of the device. Okay. Now, there's some things you have to look at in terms of efficiency considerations when you're looking at pumps versus motors, and this is a good way to kind of circle around back to pumps, which we covered a few weeks ago. In a pump, volumetric efficiency is most important. In other words, I want to use the least amount of mechanical effort as I can to get the maximum amount of fluid flow through, and that makes sense. In motors, however, mechanical efficiency is the most important thing. So I want to maximize the amount of torque or twist that I get out of my motor by minimizing the amount of fluid flow that I have to put through it in order to get that output. So really, they are doing the same thing, but backwards. So when you're designing a pump versus a motor, it's the nuance you want to deal with. Is to create fluid flow, and the purpose of a hydraulic motor, of course, is to create rotational movement, right? So here's an example of a gear motor, and this is an external gear motor. A very simple device, looks very much like a gear pump. You have two gears inside of it, and the two gears, one is just an idler, the one on the right. The one on the left is actually hooked up to the output shaft. In the middle there, you see what's called the wear plate, and the wear plate is exactly that. It is a replaceable component that is designed out of a softer material, and that's designed to save your bearings and to save your gears from wearing down. The efficiency of a motor is going to be limited to the amount of fluid escaping through the middle. Now, in this particular design, the fluid comes in through the bottom and is shunted around the outside of the case and then is deposited in the middle on the top. So any fluid that is able to get past the center is going to be lost energy. Now, you're going to need some to get through in order to form that boundary film and to lubricate the parts, but you want to minimize that as much as possible in order to maximize the amount of torque that you have in your system. So here's an example of an external gear motor. They're very robust, they're excellent speed control, they're a little bit noisy, but they deliver a really good bang for your buck, and they'll work on a dirtier fluid or a dirtier process too. So the incoming fluid acts on the surface area and causes rotation that may, you may seem it's initially counterintuitive. You think it would want to go through the middle as opposed to going through the outside, but because there is a gap on the outside as compared to the inside, the least resistance is along the outside of that casing. As a result, both of the gears turn towards the middle and fluid is rejected from the inlet at the bottom in the middle and directed around the outside. And again, this one will have one output shaft, generally on the left-hand side, and the idler gear is on the right-hand side of the motor. And the idler gear does really nothing but is a placeholder for the system. So this is an internal gear motor, or what we call a direct drive Gerotor, and it consists of an inner and an outer gear, and both of them turn. The inner gear has fewer teeth than the outer gear. As the fluid enters the housing, as you can see, both gears turn, but because there is an eccentricity in it, in other words, it's offset a little bit, the output shaft is a little lower on the casing and it's not quite in the middle. That allows for the voids to be created on the upper side. And as a result of that, as the fluid is pushed in and that void gets bigger, again, pressure is cached in for rotational movement, and you turn that pressure into RPM or into torque, right? So high pressure coming in from the left and low pressure coming out, going out on the right. And again, this is exactly opposite of Gerotor pump. So this is an orbiting Gerotor, and this one varies from the other one in that in this particular design, the outer gear is stationary and the inner gear moves. And you'll see that the inner gear actually has teeth on the inside of it, and that corresponds to the output shaft, which is right in the middle there. And the output shaft is driven as that inner gear walks its way around in a kind of a repeating oscillating pattern. Three pictures indicate the ducting and the fluid flow paths of how the fluid is directed around the motor as that interior gear turns. And of course, again, you will have one more tooth on the outer gear as you have on the inner gear, and that provides the eccentricity, and that eccentricity allows for the rotation. Again, there are very, very simple devices. The clearances on these ones are fairly close. Here we have a different example of a different type of motor, and this is used a lot in pneumatics, as well as a little bit in hydraulics too, and this is a vane motor. Now, on the animation on the bottom, you can see that the vanes move in and out of those slots, and that the interior of the motor itself is not perfectly symmetrical, but it has some eccentricities in it. Now that allows for the expansion and contraction of those chambers, which will again facilitate that pressure drop and turning that pressure into rotational movement. Okay, now these ones are often adjustable in speed and in output because you can move that cam ring around. And as a result of that, you can change the orientation and the size of the chambers. By changing the size of the chambers, you will end up changing the output of the motors. They have a good operating efficiency, vane motors, but not as high as that as the piston motors. And since they're less of a positive displacement motor, they don't really work well at low RPM. They really kind of require some of that centrifugal force in order to work correctly, because they need to maintain that seal between the vane and the outer housing to create that channel for the fluid to flow through. If you don't have that good centrifugal seal, then you'll have leakage back and you will lose power in your motor. Now, radial piston motors, because of the positive displacement aspect of them, and they achieve that, as you see in the top graphic there in that animation, which is a pump, but quite frankly is exactly the same as a motor. You'll see that there are two check valves there, and those check valves and the pistons are on spring activated. So that allows the fluid to flow in two directions, in and out of the piston. The piston acts on that eccentric cam, and as the device goes around in a circle, it creates a circular motion from the radial linear motion of the pistons. Now, these can also have a speed characteristic to them by changing the eccentricity again, and by doing that, I change the amount of travel that the pistons travel, and by controlling the piston travel, I control the amount of fluid that goes through the motor, therefore the speed and the torque. So now these motors provide a very high torque at a very low shaft speed because of the positive displacement of the rotor, and that allows all of the fluid's energy to be transported into the rotating shaft. Right. An axial piston pump is a little bit of a different animal. It has the same operating principle, except it uses what's called a swash plate. And that swash plate, the angle can be changed on the swash plate, and that will change the amount that the pistons move in and out. By changing the amount that the pistons move in and out, I change the volumetric flow through the motor and therefore control its speed and its torque. So these ones here will provide an extremely good torque characteristic right down to about 4 revolutions per minute. So these ones are excellent for inching purposes. If I'm moving, for instance, steel rollers with moving tons of hot steel, and I need to move it slowly to move it into the cutters or to part of the processing, I might want to use an axial piston motor because of the fact that I can control the speed very closely by changing the angle of that swash plate, and therefore changing the torque and the speed of the output of the motor. Another way of doing this same kind of thing is what we call a bent axis piston motor. These are quite common. They're a fairly good small package as well, and sometimes the bent axis is a design feature that makes them a little smaller than the inline axis. Again, by changing the angle of the bent axis, you're going to change the speed and the torque. That allows you to have a good varied output throughout a large operating range. And these devices are very useful in that they're fairly low maintenance for the type of torque that they develop. They have less moving parts than the inline unit and generally can come up with a fair amount of torque on a short basis. So that's an example of some of the motors that you'd be seeing in industry, the common ones. There are different types of motors, special applications, what have you, and that will all depend on the processes that you're using. But this is kind of an overview of the different types of motors that you'll be using. The radial motors, either they be them bent axis or radial piston, are by far the most common in where speed control and variable output are required. A gear motor is a great motor for consistent output, one flow rate in a pump, one speed in a motor. They work very well. Okay, well, I hope you've enjoyed this and it has been enlightening for you. And we will see you next time for lesson 6, where we will talk about accessories and seals of a hydraulic system, one of the most overlooked but critical parts of a hydraulic system overall. Thank you.